You've seen it. You can see it in the reflection on my diploma back there. You can see the reflection of the TV. It's just YouTube, just playing music. And then every now and then I'll look up and I'll see something horribly inappropriate, and I'll be like, God dang it, that shouldn't be there. So I'll have to skip it. I think this is Red Hot Chili Peppers. So anyway, which of the following is the formula to determine the standard deviation of a binomial distribution? Right? So it's designed to give you a kickstart on the test. Everybody should be getting number one right. This should be choice B. Right off the bat. You see, it's a slightly different question, same choices. Fair enough. Slightly different question because it's asking for something different. You know, it's asking for the standard deviation of a binomial distribution. Right? But it's still the four choices, same four choices, same order. All I did was I took a screenshot of these four choices and put it on Blackboard. So on the actual practice test up there, I asked for the mean of a probability distribution. Right? So if I'm going to vary it up, this one I might ask for the standard deviation of a probability distribution. Oh, actually, sorry about that. This one's actually nothing. This is a red herring. This is a trick. I can't even write trick. It's not actually a formula. This is the mean of a probability distribution. And this one is the mean of a binomial distribution. Okay. So those are what the four choices are. So how this act. I can look up surveys in a little bit. Once I'm done with this part of the lesson, I'll take a look at all that. So yeah, just have a note of this. Have it available. Every test is an open notes test. Have your notes ready to rock and roll. There's no reason why you would need to Google anything. I'll tell you, everything that you need in order to be successful on this test is in your notes somewhere. Right. So if you have good notes, access to them, then you're going to be good to go. Right. 4 conditions that must be satisfied in order for a distribution to be considered binomial. First, you got to have a fixed number of trials. Second, you have to have a fixed probability. Third, you have to have independent events. And lastly, you have to have 2 outcomes. And those 2 outcomes would be success or failure, but it doesn't really matter. Those 2 outcomes could be up or down. It doesn't make a difference. Yes, yeah, this is part of the review. It's already posted on Blackboard, and the answer key will be posted up along with it. Number 3, the following is if the following is a probability distribution. Compute the mean, the standard deviation. If it's not a probability distribution, explain why. All right. So in this case, it's actually not a probability distribution. All right. In order for a distribution to be considered a probability distribution, the sum of the P of X values must be equal to 1. Right? So that means all of these values have to add up to equal 1. Right? So you can check for that. But even before you get to that, and again, this means something. Even before you get to that, you got to make sure each individual probability value is an appropriate probability value. Each probability must be between 0 and 1 inclusive. All right. So it can be 0, it can be 1. Each of the probabilities can be 0, can be 1, can be anything in between, can't be anything beyond. Right. So definitely can't have negative numbers. Definitely can't have a value that's bigger than 1. Right. Now, a natural question here would be, all right, well, what if it was something I could find the mean or standard deviation to? What would I do then? Right, that's an excellent question. I'm glad you asked. All right. So if that's the case, then what you would need to do, or what you would probably, I would say, want to do, maybe not need to do. And I'm going to zoom. You'd go to the probability distribution calculator. And that's assuming that you didn't want to do all that stuff by hand. That's up to you. But if you open the calculator that I created, probability distribution, you have a few different options. One is the graph of the probability distribution. You see a table of values that's already in there by default. You'd have to change those numbers, which I can do in a sec. Right? But then after that, it'll give you the mean and the standard deviation. It'll also give you the usual interval if you need it. Right? And this question isn't calling for that, so I'm not worried about that. Right? So what I'll do actually is, while I'm here, I'll just type these numbers in. It's just going to be easier to type them in on the old computer. And I'll even put the incorrect values in. 2 and 3. Just so you can see. Because people fall for this trick all the time. And I gotta say, just like I pointed out before with that first question, how that last choice is not really a formula, it's a trick. I tend to telegraph my tricks just because I'm kind of proud of them. Like I usually stumble upon a trick. I'm not so creative that I'm sitting there being like, oh, how could I trick people? It's more like, oh, that's a tricky one. Completely by accident, but that's a tricky one. And so when it happens, I'm kind of proud of myself. And so this is what's happening if we can kind of make it look a little nicer. It's a little iffy. I'll just hit the home button a little bit better. So this is what the calculator is displaying graphically. And so this should be kind of a red flag, because any probability distribution graph should always be above the x-axis, all right? But also should never be above 1, all right? Now, some of us are a little bit more savvy with the tech than others, and that's perfectly fine. For those of you who are a little bit more savvy and willing to play around with things like graph settings, what you can do is click on this little wrench and change your y-axis, because y represents the probabilities. Change your y-axis so it goes from 0 to 1. And then just kind of scroll back a little bit from there. And then you can see the cutoff here for 1 at that high end. That y value of 1, you can see that there's some graph that goes above 1. And you can see that there's some graph that goes below 0. that would be a visual way of determining that you're looking at a distribution that's not a probability distribution. But here's the issue, the big issue. And students run into this all the time. And this is what I'm talking about. On the test, people don't, like anxiety kicks in. So that's always a thing. But sometimes people just aren't thinking. And they see data set, type in the data set. What does it ask for? The mean and standard deviation. All right, boom, mean, negative 0.0382. Standard deviation, undefined. Just write it down, move on. All right, not right. Well, especially the standard deviation, because if it says undefined, that should be a red flag. All right, so a second red flag. All right? But it is possible to have a mean that's negative, but your standard deviation should never be undefined. All right, so it gives you a little bit of an indicator just by looking at the problem whether or not you're on the right track. Now, if it were something like let me just change this to a 0. If memory serves, if both of these are 0, it works out. Then you're looking at something that would actually check out and give you some values that are reasonable. That's a different story. But you do need to make sure that your Y column or your P of X column, if you're looking at the handout, adds up to 1. All right, so on Desmos, the way to check that is to use the total function. All right, so all I would have to do, let me just move this over a little bit, is just type in total and then Y1 and see if that gives me a value equal to 1. So even with those numbers that I just changed, I made them zeros instead of -1, positive 1, -1. It still isn't even giving me a value that's equal to 1. That Y column better be equal to 1. Otherwise, it's not a probability distribution. And so therefore, there's no work to be done except for your explanation. So this was the original data set. Sorry for scrolling, but this is your original data set. The total is nowhere near a 1, but you shouldn't even get that far because once you see that there's a negative and a value greater than 1, that's your indication that it's not a probability distribution, and therefore there's no work to be done. All right. So let me pause. According to the NPF poll, 60% of American consumers prefer Hyundai over Kia. Let X equal the number of American consumers out of a random sample of 50 who prefer Hyundai over Kia. What is the probability that at most 20 adults prefer Hyundai over Kia? Right. So this goes back to number 2, and it's actually the reason why I asked you for number 2, so that you can actually have a ready-made list in order to have a complete solution for something like number 4. All right. There is a fixed number of trials. I'm going to use my highlighter. Fixed number of trials would be the sample of 50. The fixed probability, 60%. Independent events and 2 outcomes, those are kind of a little bit more intuitive. The 2 outcomes, I think that's kind of obvious, but only once you've read the problem. That's Kia or Hyundai. I could actually still use my highlighter there. Those 2 possibilities, you have a choice, Kia or Hyundai or Kia. The independent events, that goes back to what I was saying for that multiple choice scenario, where if you select a choice for one question, it doesn't mean that you can no longer select a choice for another. It's kind of like the idea that if a person chooses Hyundai over Kia, like you go up to a random person on the street, you may not like either of them, but if you're stuck with having to choose one or the other, Hyundai or Kia, just because one person selects Hyundai doesn't mean other people can't select Hyundai. All right. So they are independent events. So once you determine that, then it becomes a binomial probability situation, in which case we can use our binomial calculator, which is hugely important. because once I recognize that this is the binomial calculator situation, everything else gets done on that calculator. So I just go right to the top. Number of trials, 50. Probability of success, 0.6. All right. Now, what is the probability that at most? That's the only thinking part of this. At most, 20 means the X value has to be between 0 and 20, all right? But it really just means that X is less than or equal to 20, all right? So the lowest possible value it could be is 0. So the minimum number of successes would be 0 because out of the 50 people, maybe nobody selected Hyundai, right? The most number of successes would be 20. And so all I need is the probability for that, which is automatically computed for me. So the probability that X is less than or equal to 20 is approximately 0.00336. So hopefully you can see here that I'm not asking you to do any computation. If you remember the video on binomial probability from over the last week, you probably remember a lot of setup and not so much computation by hand. There really isn't anything to be done. We don't have to do the work. The computer or the calculator is doing the work for us. That's the whole idea. That's all we ever want. That's all I ever want for you. All right. Number 5 is related to the same scenario, so it's still binomial. Determine the number of American adults you would expect to prefer Hyundai over Kia. Expect is another way, expected value anyway, is another way of saying the mean. So that's mu equals NP. So I could write it, like I could say 50 times 0.6 and then use a calculator to figure out that answer, but I'm not going to. I'm going to sit tight on that for a second. Because I could also say the standard deviation, the square root of NP times 1 minus P, is equal, oh, that's a large eraser, is equal to 50 times 0.6 times 1 minus 0.6. That's all well and good. And again, I could crunch those numbers, but if I know my calculator, like I think I do, / I made this calculator, so I better know it. It's all there, waiting for you. Pretty nice. Now, if I were you, because this stuff is not off limits prior to the test, you have access to it. It's not secure. It's not hidden in a vault anywhere. Why not make your own copies of these? You got your Desmos account, hopefully. If you don't, make a Desmos account, for crying out loud. Save these calculators and then add on your own bells and whistles. Because the next thing I think that makes sense would be to have usual, unusual. Like I would want my calculator to automatically compute the unusual values for it. I mean, I'll just do it now by hand, but I would make that a little add-on. So, and honestly, if you look at it and say, well, I don't know how to do that. Hey, that's all good. I was there too. In a lot of cases, I was there like 2 months ago. All you really need to do is look at some of the calculators I've created and worst case scenario, do some copying and pasting, right? Because I have mu minus 2 sigma and mu plus 2 sigma saved in another Desmos, in the probability distribution Desmos. So just copy it from there and put it in here. And now you'll have the usual and unusual values. All right. I just did it manually real quick. So we're looking for, again, mu plus or minus 2 sigma gives us the interval of 23.072 to 36.928. This is the usual range. And you see how I go back and forth, usual range, usual interval means the same thing. All right. So therefore, 3 dots in the form of the triangle means therefore 10 would be, it's a test, so I'm not expecting you to go nuts with it. 10 would be unusual. All right. I'm checking the chat here. Yeah, exactly. When you save, so the question is, if you save it, you just edit the numbers. Yeah, when you save the calculator, all you do is you just go in and change the numbers. All right. So for this test, all you would need is the binomial and the probability distribution calculator. The 2 calculators from Unit 2, and that'll get you where you need to go. All right. There won't be anything on the test related to specific calculators other than those 2. Yeah, no problem. All right. So number 6, 12 marbles are placed in a bag. 3 are white, 1 is red, 2 are black, and the remaining marbles are green. All right. What is the probability that a marble selected at random is either white or green? All right. So that's an addition rule kind of situation. There's a couple of different ways of handling it. Since it's a small sample, you could actually, honestly, you could just draw out a picture if you wanted to. The problem is, if I wanted to draw out, here's my first white marble. Here's my second white marble. Here's my third white marble. So if you get the idea that, like, oh, you're not drawing anything, dude. I am. I'm just drawing it in white. You know, so it was there. It wasn't showing up. Right. So let's not do that. Let's use a more probability-based technique. Right. So the addition rule, first off, I got to make sure it's not mutually exclusive in that there is an overlap. You can have a marble that's both red and black at the same time. What I'm looking for here is the probability that a marble is going to be white plus the probability that a marble is going to be green. So white, well, there's 3 of those out of the 12. The green, different story. You just got to figure out how many there are because they left that open-ended, kind of. We have 12 overall. 3 are white. 1 is red. 2 are black. And the rest are green. So that's going to leave us with 7 green. So that's telling us that we have 7 over 12 that are green, giving us, actually, that can't be right. I must have screwed something up. Red, blue, 9, 8, 7, 6. I got the idiot. Doofus. Yeah. So we would get 9 out of 12, and that's fine. You don't need to simplify fractions. You can leave an unsimplified form. The other thing is you could also kind of look at, right, if we're looking for what's a marble is white or green, you could just eliminate the things that you don't want, which would be the red and blacks. And whatever's left is the ones that you would keep. You know, so I'm saying if I want white or green, then I don't want the 1 red and I don't want the 2 black. I don't want 3 marbles in total out of the 12. That means I want 9 of them. All right. We're going to be going into breakout rooms for the tech assignment in a little bit. Okay. So number 7, very simple. When it comes to conditional probability, probability of getting a female is the given. So we're only focusing on the female. If I want the probability of an individual, oh, typo for somebody. There should be the letter P in front of this. Probability of self-taught given female. Right? So what I'm looking for out of only the females, because that's the given, I'm looking for the probability that an individual is self-taught, right? So there are 12 self-taught individuals, and there are 72 females overall, and so that's our probability. Conditional probability should be a nice, easy problem to work on. When it comes to taking the test, it should be a quick hitter. The issue when it comes to conditional probability is people often get it backwards. You know, instead of highlighting the females, they highlight the self-taught and get 12 out of 31 rather than 12 out of 72. All right. So you just got to be careful about that, but it ends up being a matter of, you know, just patience and studying. All right. Number 8, suppose a coin is flipped and a color is selected from the following set: black, white, blah, blah, blah. Create a tree diagram. Oh, sorry. Another typo. I actually changed this one right before the class started, so this one's on me. Well, they're all on me, but this one's really on me. Suppose a coin is flipped twice, and a color is selected from the following set. All right, we want to create a tree diagram for that. All right, so the way the tree diagram would play out, or you could list the sample space too. If you're typing out your response. A handwritten response is good for a tree diagram is good for that. The sample space is good if you're typing. Okay. So if you're flipping a coin twice, I would say my outcome for coin 1, or the first coin flip, would be heads, tails. Then from there, I would have coin 2, which would branch off from coin 1, also giving heads, tails. All right. Then from there, I would branch off, and this is the part where it gets a little kooky and can be messy. And what happens is people tend to want to go for a sample space once they start going down this road, is you get into the color. There's black, there's white, there's red, there's orange, there's green. So for each one of these, there's a different color. So black, white, red, orange, yellow, green, blue, and purple. All right. And so what you'd have to do here, once you realize that you totally misjudged the amount of space that you have, like I just did, is you'd have to either rewrite the whole thing or start shrinking things around in order to make it all fit. All right. Which can be definitely more trouble than it's worth. And so, but you can get it in there. It's not going to be pretty. Right. So what I would do is I just kind of move this down a little bit, move this down a little bit, change the angle. Tuck that in there. You see what I mean? It's like I said, it ain't pretty. And actually what I would do here is delete this one, copy, paste this one, and just change my my heads to a tails. And then I would work to reorganize it. And usually reorganizing just means kind of shrink it down even more. All right. So I'm kind of doing it this way, sort of like in a cavalier sense, just to kind of, I don't want to say dissuade you from creating the tree diagram, but more so to kind of encourage you that maybe the sample space approach is the way to go. because if you're looking at the different possible outcomes in the form of a sample space, it's usually just a matter of saying, all right, well, I got a heads and a heads, and my first color is black, right? So heads, heads, black. Then I could do heads, heads, white. Heads, heads, red. Heads, heads, orange. Heads, heads, yellow. Heads, heads, green. Heads, heads, blue. Heads, heads, purple. All right. And then, and you know, I'm not oblivious to the fact that my job here is a whole lot easier because I'm doing this digitally. That's an important component to how I'm making this as easy as I am, because this would take a whole lot longer if I had to do it out, you know, with pencil and paper and all that stuff, right? But if you're typing it, you have the benefit of copy paste, right? Because what I would be doing here is, okay, the next up would be heads, tails, right? And then the black, the white, the red, the blah, blah, blah. So I would do a copy paste here. Even if it's something that I typed, I'd copy paste, all the heads in the middle become tails. And then for the next set, where it's tails, heads, and so on, I duplicate everything, copy paste, and all the initial head values become tails. And so that would be the sample space. So you don't have to do both. It's an either or. You don't have to do them both, one or the other, but you're going to have to do one of them, like I said. Okay. Neither of them are pretty, but I like the idea of a sample space, especially for an assessment that you're taking online, because it gives you the ability to use copy paste. All right. Number 9, 12 marbles placed in the bag, 3 white ones. So same question, same idea as number 6. But this time it's what's the probability that 3 marbles selected at random are all white if the marbles are selected with without replacement. All right. So we're looking at the probability of getting a white marble and a white marble and a white marble, which would be the probability of getting a white times the probability of getting a white times the probability of getting a white. All right. So we know that there are 3 white marbles. There are 12 overall. If I select one at random, it's 3 over 12, 3 out of 12. All right. If I select one, I assume success. That means I got one of the white marbles. That means there's only 2 white marbles left out of 11. If I got one of those 2 white marbles out of the 11 available, that means that there's only 1 white marble left out of the 10 remaining marbles. And so we're looking at 6 over, that would be 1320. All right, so it's multiplication. All right. And then the last question, how many events are in the sample space of 3 flips of a coin followed by 4 rolls of a die? That goes way back to the beginning of the unit. So all you'd have to do is take the number of outcomes for the flip of a coin. So 1 flip equals 2 outcomes. And then the number of outcomes for 1 roll of a die. That's 6 outcomes. And so we would write 2 to the 3rd power, because your you're flipping the coin 3 times. So I'll use my highlighter. So the 2 outcomes raised to the 3rd power, and means multiply 6 outcomes. And that's another set of outcomes, but this time associated with the roll of the die. But you're rolling the die 4 times, so it's raised to the 4th power. And 4 rolls of die. And so this is straight number crunching, nothing too fancy. So 2 to the 3rd multiplied by 6 to the 4th, and you get 103.86. 68, sorry. So 10,368 outcomes. So you definitely would not want to have to draw out a tree diagram or a sample space for that kind of problem. That would be pretty